So today we're going to talk about protecting metals from corrosion. It's a real problem with metals because they're reactive, and if you look at the standard reduction potentials, you'll see that a lot of metals actually release energy when they give up their electrons. So we don't want metals to do that. Usually we like metals to stick around, have good structural integrity. So we look at what happens when metals give up their electrons and how we can prevent them from giving up their electrons and stay as a strong, shiny metal as opposed to just the rust. Yes, question?
Why you couldn't have had the time to mark the class assignments we did yesterday? Could you go over a couple questions?
Certainly.
I don't have it anymore. I handed it in, but
I realize that. Not everyone's handed it in yet, though. You were ahead of the time.
until like the last minute of the last block, which is like, no, it's okay, take it.
Yeah.
Okay. Good, you worked quickly then. Alright, so let's consider iron. Solid iron is a good construction material. It's strong, and it also is flexible. It still retains its strength even though it's flexible. So it's a good construction material. It's strong, but it's also flexible, which is the two things you want from a structural material. You want to be able to take a lot of load, hold a lot of strength, tensile strength, whatever. But if something happens, if the building shifts or a different weight goes on to the building, or there's an earthquake, you want the material to flex as well too. And iron is really good that way. It flexes under a lot of strain, but doesn't lose its strength when it undergoes flexing. Iron, however, tends to lose its strength rather rapidly when it corrodes. So, corrosion not only destroys the strength and the flexibility of the metal, it makes it essentially useless as a construction material.
Can you wait to have in your class? That's good.
Alright, so it destroys its strength, destroys its flexibility, and its goodness, its value as a construction material is in fact lost if there's corrosion. Now this process of corrosion can happen to any metal. All metals corrode. Iron is just famous for corroding because it happens so often that we have a special name for the corrosion of iron. It's called rust or rusting. And so rust is given to the corrosion of iron, and it goes from being a shiny, strong material to this dark red, brown, flaky material. That's really almost good for nothing. Okay. So it's red, it's brown, it's flaky. So all the things we like about iron are really lost when we get to rust. It's not very good for anything in terms of construction. So our task then, as chemists, is figuring out how we can prevent this reaction from occurring, and we'll do that by first off understanding what happens when iron corrodes. Okay? Now this corrosion reaction, this loss of integrity and strength, happens to a lot of metals. Of course, iron is just a really good example of this. Well, you know that iron likes to give up its electrons. So iron solid will give up 2 electrons and become iron ion, so the ferrous ion, and there's a potential, an oxidation potential associated with that. What's the oxidation potential for this reaction? So you need to look in your chart of standard reduction potentials and read, instead of the reduction potential, the oxidation potential. Good, you're getting your chart out, you're having a look at the last chart. And what do you see? Your oxidation potential for iron. Iron going to iron 2 plus.
Very high.
Well, we need an actual number here. We need a number because when we talk about whether a reaction is spontaneous or not, we need to add the number for the oxidation to the number for the corresponding reduction and see if they add up to a positive number. What do you got? 0.45. Okay, so all by itself, that tells us that, well, iron likes to do this, right? Has a positive oxidation potential. So already the deck is stacked against us in terms of preserving our iron. Now, iron, of course, will not give up its electrons unless there's something to give up its electrons to. Right?
It needs a reduction.
Wow.
Yes, it needs a corresponding reduction. So what do you think might be present with the iron that can allow reduction? Water is present, and also
Hydrogen.
oxygen is present. So we've got water and oxygen present. Obviously there's going to be lots of materials around that can be reduced that can pair up with the iron. And so this reaction is well understood, and you don't have to memorize the reaction, but I'm going to write the reaction on the board so that you can sort of see it and kind of we'll look up and see what's going to happen. All right. So let's look at the presence of oxygen. So we'll take an oxygen, and in the presence of water, and in the presence of 2 electrons, and we make 2 hydroxide. Okay? So we're balancing with a half because essentially we're saying that half a mole of oxygen with a mole of water can undergo this reaction. So don't be thrown off by the half. We're just saying half a mole. Okay? It's going to go through this reaction.
We could double it.
Yeah, we could double it. Do we have a potential for this reduction? Yeah, we do. So look for a reduction reaction involving oxygen and...
Oh, no, I do. It's 0.20.
0.20 volts. Okay. Now, do you see the problem? Why the oxidation of iron is such a problem? If you have oxygen present and the iron is wet, in other words, there's water present, then you have what kind of reaction?
Reduction.
Well, you've got a reduction
Oh, yeah.
reaction and an oxidation, but overall, what would we say about this
Redox.
process? It's a redox reaction.
It's resting. I don't know, guys.
It's reducing.
It's spontaneous.
Oh, yeah, that was...
Right? Why do we know that this pair of half reactions is going to add to be a spontaneous reaction?
Because iron naturally gives up its electron and then reduces spontaneously as an oxygen oxides. Yeah.
So in other words, wet iron in the presence of oxygen, in other words, anywhere on the surface of this earth, is going to spontaneously rust. In fact, it seems to be remarkable that we're able to keep iron around at all. If any time the thing gets wet, it's going to rust. So we already know this instinctively. You know if you have something iron, and if you leave water on it, there's more chance that it'll rust, right? Like a poor quality iron object often rusts when we leave water on it, and now we know why. It's a spontaneous reaction with the oxygen dissolved in water with the iron. So we ask ourselves then, how can we prevent the iron from rusting?
Alloys,
Keep it dry.
coating.
Alright, and our first solution was?
Oh, keep it dry.
Yeah, dry. If you keep the iron dry and clean, that's going to help right away, because you're going to keep the water away from it, and any dirt or any other ions that are going to be on it that are going to encourage the rusting, they won't be such a problem as well too. That's going to help. Is keeping it dry and clean going to be enough?
No.
On the surface? No, it's not. Moisture is almost everywhere.
In the air.
In the air. So keeping it dry and clean is going to help. Polishing it is obviously going to help keep the surface clean. That's what polishing really does. What else might we do?
You could just let the surface rust and then it'll form a protective layer.
That's a good idea. Winnie suggested that what we can do is just let it rust. And then the rust will coat the outside of the iron, and that'll form a protective layer that prevents more rust from occurring. Does that work?
Not all the time.
No, it doesn't work.
Sort of.
Why doesn't it work? In fact, people who know
It
cars
flakes.
really well, as soon as they see a spot of iron, of rust, they often get rid of that. They don't leave that rust on, because they know something, just empirically. What do we know about rust? When something starts to rust?
It flakes.
It's like apples.
It flakes.
It flakes off.
And it
See, answers
spreads.
Yeah, the rust seems to spread, doesn't it? It does, because the product of this, iron hydroxide, catalyzes its own formation. Yeah. Well, the reason it does is you get an electrolyte solution with lots of negative ions around, and they help balance the charge of the new iron ions being made, and so it makes it easier for iron to give up its electrons. Not good. Okay? So it turns out that letting it rust is actually not helpful at all. If you let the thing rust, you don't get a coat. Now, it wasn't a bad idea. Let's consider aluminum. So quickly grab your table of reduction potentials and take a look at aluminum. And we use aluminum for pots and pans, so constantly in contact with solutions and acidic solutions. We use it for airplanes, so constantly in contact with moisture and oxygen, and yet still we don't seem to worry so much about aluminum. What do we notice when we look at the oxidation of aluminum?
1.66 volts.
1.66. Now, aluminum should just frankly disappear in front of us. This same reaction can happen with aluminum, right? Add another 0.2 volts on that, almost 2 volts of encouragement. This thing only has 0.6 volts of encouragement, happens all the time. Aluminum should frankly disappear right in front of us. Our can should puff into a smoke of aluminum hydroxide. Okay, a couple of things are happening. Aluminum doesn't do that. What is some of the reasons? It does make a barrier. When aluminum oxide forms, it's different from the iron oxide or the iron hydroxide. It makes a barrier that actually clings to the surface of aluminum and prevents new aluminum from oxidizing. So aluminum does this, and to a smaller extent, zinc does this as well. Not as much, but yes, it does do it as well. The patina coats the copper, the green copper patina coats copper, and it's harder for the copper underneath to become oxidized. Iron, on the other hand, I've said a couple times, it
Catalyzes its own demand.
catalyzes its own formation and it flakes away. Yes?
Except in salt water. Aluminum, but with salt water, the zinc bar.
Oh, yes, from. Okay, so in certain conditions, salt obviously accelerates the rusting process. Why?
Because salt bread.
Yeah, it's got salts, right? Salt's presence balances the ion charge, makes it easier for the electrons to flow, and accelerates the rusting process or the corrosion process. So it wasn't a bad idea letting it rust, because that certainly works for aluminum, and as pointed out, works for other metals like copper and zinc. They get a coating on the outside of the oxide, and they don't wear away really quickly, but it's not going to work for rust. Okay, so what else can we do?
You can coat it with a plastic.
Coat the rust, or coat the iron. And coating can be plastic, it can be oil, and what do we use most often though to coat the rust?
Other metals.
Yes? Yeah. What do we use most often though?
Magnesium.
No, what do we do most often with iron? Paint it.
Oh.
Wow. We paint it, right? You take a car, you don't leave a nice shiny car, you put a coat of paint on it. And if that paint chips, what are you supposed to do?
Repaint it.
Yeah, you get paint on that chip right away. Why?
Because it'll rust.
It'll rust right where the paint chip is. Okay? So we paint it. And then, as Wendy pointed out, we coat with other metals. So a layer of zinc, or a layer of aluminum, or a layer of gold would really protect our car. Unfortunately, we can't really afford to gold paint our car unless we're a Bond villain, so we stick with paint. All right? And so the paint coats it, prevents oxygen and water from getting at the iron. And back when I had a car in Ontario, I used to go to a place every year and had this gloop sprayed on the underside of the car to stop it from rusting. And the gloop was just a mixture of oil and tar. And literally, they put the car up in a hoist and they simply sprayed it down. And you did that every year. And you paid your money, and that helped prevent your car from rusting. Because with the salt on the road, you really got an accelerated rusting process. Not so much a problem in BC because we don't often salt our roads because it doesn't freeze so often, but it does. And when the salt gets on the road, if that gets on your car, it'll accelerate this process and increase the rust. So washing your car frequently to get the salt off is a good idea. Okay? There's a place in the States called the Bonneville Salt Flats that people go to race their cars. But there's a big warning sign when you get there. These are salt flats. you race your car here, you're going to pay the price for it as the car rusts away over the next little time unless you wash all that salt off and make sure you have no paint chips. Okay, coating with other metals. Let's talk about this. So these all make sense. We simply prevent oxygen and water from getting at the metal so it can't rust if it has nobody to pass the electrons to, and so the iron stays intact. If you get a paint chip or something, you fix it up. How does coating with another metal help?
Because it won't oxidize?
Yeah, you can't oxidize the iron if there's another metal on the outside. So you pick a metal that's more difficult to oxidize, or one that oxidizes and doesn't flake away, like zinc. Okay? In fact, this coating with zinc makes what we call galvanized sheeting. Have you heard of galvanized sheeting? It's corrugated sheeting, often used in third world countries, less developed countries, to make roofs. And it looks like little star patterns on the sheets. That is a layer of iron usually with a thin layer of zinc on top. And it's called galvanized because the process is galvanization, named after the guy. And what they do is they attach an electrode to the piece of iron, and they make it accessible to zinc or dip it in zinc, and the zinc coats the iron on literally almost a microscopic level. And that layer of zinc prevents the iron from rusting. And so those iron roofs would rust away, but the layer of zinc protects them because, of course, zinc oxide clings to the zinc and doesn't let the oxygen through. And that protects the iron. So galvanized works.
But it's all metal, right?
So galvanized.
Isn't galvanizing just...
It's coating with a layer of zinc.
Yeah.
Right? And obviously it protects the iron, and away we go. Okay? There is a slightly more complicated method of protecting iron that Ms. Vito referred to, and it's called cathodic protection.
The zinc bar or something?
Yeah.
Is that only for salt water?
Nope, it can be used in all kinds of ways. One of the fun things I did when I had a car was I used cathodic protection. It was really fun trying to explain to the mechanic what I wanted him to do with the bar of zinc, but he eventually did it for me, and he attached it to the car. So cathodic protection. Now, what do we know about cathodes? What is a cathode?
It gains stuff.
Wait, red cat.
That's right. So a cathode is the site of reduction.
There's also an ox here.
Right? So the cathode, let me get this right. A cathode is the site of reduction. Okay? So if you've got two metals, do you want iron, and you're trying to preserve your iron, do you want iron to be the anode or the cathode?
Cathode.
Cathode.
You want iron to be the cathode. How, if you have two metals, can you make sure that iron is the cathode?
Higher
One with a
potential.
high reduction
Excellent.
potential.
If you get another metal next to it where its oxidation potential is greater than iron's, then it will oxidize first, making iron the cathode, and you will keep your iron's electrons or gain electron at the iron level, at the iron side of it, rather than have the iron be oxidized.
And zinc must have a high reduction potential.
Excellent. A higher oxidation potential.
Oh yeah.
Right? You want iron to have the higher reduction potential so that iron is the one that gets reduced. Alright, so you attach a more easily oxidized metal. And the metal of choice for this is
Lithium.
aluminum will work, but the problem with aluminum is it's a little too good at forming that layer of oxide on the
What
outside.
about lithium though? But it has like it's
What's the
not
problem with lithium? Lithium is much too good at giving up its electrons.
So it's gonna. Oh,
Right?
what if like you make a car out of like iron and like lithium, and the electricity generated by the reaction will like
We'll fry the driver, so that's
No.
not a really good idea. Okay.
will drive the
So we're
car.
going to attach an easily oxidized metal, and the suggestions are good. What about aluminum? Well, aluminum gives up its electrons very easily, right? We saw it's got a oxidation potential of 1.66 volts, but its coating is the aluminum oxide coating coats aluminum so well that it's difficult to get it to give up its electrons. Zinc does that, but not quite as well as aluminum, so it will give up its electrons a little bit. Lithium gives up its electrons even easier than aluminum, doesn't make that coating, but the problem is it gives up its electrons so easily, it's not going to wait to pass them to iron, it's going to pass them to the next passing molecule of anything, carbon, oxygen, anything. Lithium is just way too reactive, so it won't do us any good. Right? So zinc is kind of the right level. It's easier to oxidize than iron, but not so easy that it disappears right away, giving its electrons to just anybody. It will donate its electrons. So you attach a more easily oxidizing metal, for example, zinc, and the block of zinc simply must be electrically connected to the iron. So if it's an iron ship hull, for example, it doesn't matter where you put the block of zinc, as long as there's an electrical connection through to the iron. So some people attach it on the outside of the ship, just on the inside of the hull. If you go down to the marine supply store, they have blocks of zinc for sale. Yeah, you go down and you buy a block of zinc, which is where I got a block of zinc, and I attached to my car. I had one kid who used to go down to the marina and sail. I'm like, bring me back a block of zinc. The next day, here's a block of zinc. Took that to my mechanic. I'm saying, attach this to my car. He was like, what? I'm like, just screw it into the frame of the car. That's all you need to do. Right? And he did. He screwed it into the frame of the car. And there's my block of zinc on the bottom of my car, protecting it from rusting. Okay? All right. How does the zinc protect the iron? Well, when there's a redox reaction, the zinc acts like the anode and therefore donates electrons to the iron. So zinc acts like the anode. And so at the anode, you get zinc giving up its electrons so that iron can be the cathode. Now this method is even used for things that have to remain in contact with the environment under uncontrolled conditions for a long period of time. Can you think of a use of iron where the iron must remain in contact with the environment under uncontrolled conditions for a long period of time and over great distances? Sorry? Buildings is true, but in buildings you can coat the iron. You know, in concrete or whatever, you don't have the iron actually exposed to the soil or to the thing. But think of something that over a long distance and a long period of time, this iron remains in contact with the environment.
Plumbing.
Did you say? Freight boats, yeah, that's true, and they use cathodic protection. You can actually see them. If you look at the hull of a freighter, you'll see the lump of zinc that they replace almost every voyage.
Whoa.
Yeah, they go out there and some guy screws in a new one almost every voyage. Can you think of something that tends to be made of iron, and it is in contact over a long distance as well as a long period of time? Trains? True, but they're not so much in contact with the environment, right? Because they're a little off the ground. This thing is in contact with the ground.
Oh, telephone wires? No, landlines. Landlines.
Landlines? You're
Or
on the
like
right
the
track.
electricity thing.
Not fences, but underneath the ground.
Pipes?
Pipes, pipelines, right? Think of a pipeline. It could run for hundreds of kilometers, and it's in contact with moist soil and atmospheric conditions or whatever, even in the ground. How do you protect it? You lay a line of zinc next to the pipeline, and every few intervals you attach the zinc by a wire to the iron pipe, so that you have cathodic protection along the length of the pipeline.
So
Otherwise, the pipeline might just rust out and the oil or whatever will just spill.
Do they
So
just
this
like
is used
dig
for
up?
pipelines.
So
Sorry?
do they just like dig up the?
When they're laying the pipe, they lay a line of zinc next to it.
Yeah, but the zinc will eventually be
Yeah,
depleted.
zinc will
So
eventually,
do
and
they
either the
just have
pipe
to,
will
like,
rust and
so
leak, or the zinc has to be replaced.
So they
Absolutely.
just dig it up like every.
It depends on the type of pipeline, the amount of zinc, and how long the pipeline's been there. But yeah, the zinc wears away eventually, and so eventually the pipeline will leak if the zinc isn't replaced. Yes.
Is this used in like all underground piping or
It-
just
if-
like oil piping?
The ones made of iron that are susceptible to this. This is one of the main methods. Sorry.
It could be any like type of pipe.
Oh yeah, it doesn't have to be oil pipes. It could be a water pipe, for example. Now they use a lot of plastics for piping. So you wouldn't obviously need cathodic protection, but iron is used still for today in piping. And I've seen them, laid pipe, and then there's that line of zinc
I
beside. I've
thought they
seen
use
pictures of
lead
that.
for pipes.
Lead for pipes?
Yeah.
Not usually, because lead is poisonous.
Poisonous.
So we don't usually use it for pipes, because the water will pick up lead as it goes through, and then the water has lead in it. And we usually don't want lead in our water, no matter what we're using it for, irrigation or drinking. You don't want lead in that.
Unless it's a heavy, what's it?
Like waste?
No, the water where it's like
What about
heavy.
oil?
Hard water, yeah.
We could. It's probably more expensive than iron. The reason it's been used historically is it's easier to work, is it's softer, so it's easier to make into whatever shape you want. But now we can just smelt the iron at high temperatures, so it's not a problem. And iron's cheap, because the earth is made of it. Okay.
What's the Latin name for iron? No, what's iron? What's iron? No, iron is PB. Okay, plumb. This is where we get the word plumber from. It's from the Romans who used lead pipe. Oh my gosh.
Plums are near lead. Where do we get plums from? Rarely do
All right, for example, oil pipes are laid with a long wire of zinc, and the wire of zinc, of course, is attached specifically to the oil pipeline at reasonable intervals. And so it can donate its electrons. The zinc is sacrificed. Another name for this is a sacrificial anode. Why sacrificial?
Because it's giving up its body.
That's right. So zinc is used as a sacrificial. So we call it a sacrificial anode. Okay? Sacrificial anode because it's used up in order to protect the iron. So it's a sacrificial anode. Okay. Now, so we talked about different ways of protecting the iron. Just to summarize, we need to keep the oxygen and the water away from the iron because the iron will rust. It will undergo this reaction and it will rust. And in fact, the book, as you read your textbook, the book will show how if there's a chip in the paint, and this is of course the solid iron, you will get oxidation occurring. One of the things to note is that the oxidation doesn't necessarily occur here where the chip in the paint is. The oxidation often occurs at some distance away where the iron is giving up its electrons, and the electrons are flowing to the surface where they meet the oxygen and the water and get your hydroxide. Right? So often what's happening is you'll notice if you see cars rusting, is they don't rust right at the point, they often rust around the point. You see that? And that's because all around here, the iron is giving up its electrons, which flow through the iron, because it's a conductor, to where the paint chip is, and then where the paint chip is where you get the rust forming, where the electrons are finally meeting the iron hydroxide and making the rust. So the rust, it often forms all around the paint, where the chip in the paint is. It's not that one spot that rusts. The rust usually makes a nice circle that grows all around the outside, because the iron all around is just giving up its electrons and sending them down to meet with the oxygen, because it's so spontaneous. Okay. Another reason why rust is so bad and it flakes off is rust isn't one thing. Rust is a combination of iron hydroxide and iron 3 hydroxide. Because you know that iron has more than one oxidation state. So it's not even the same chemical. Also, there's water mixed in with the rust. And there could even be some iron oxide and some iron 3 oxide present as well too. So rust is this mixture of materials with water. So that's one of the reasons it flakes. It can't make a proper crystalline structure, is it's a mixture of materials. Most of it is iron oxide, but a lot of it will be iron 3 hydroxide. Right? So it can't even make a nice coat. Like zinc oxide is just zinc oxide. It's a nice chemical. Right? So it can make a nice little bit of crystal lattice on the edge. Iron can. It's iron hydroxide, and not only that, it's often hydrated. It's often bound up with water. So it has a real difficulty forming a crystal structure, and it doesn't. It just forms these brown amorphous flakes because it's a mixture. It's not a pure substance at all. And that's part of the problem with iron. It doesn't make a pure substance when it rusts. Interesting story. In the Parliament buildings in Ontario, when they put them up, about a century and a half ago, they put a copper roof on, and of course the copper roof is on to make it look like these old buildings in England, which I think they originally put on copper roofs because the copper was shiny and it gave the building a nice shiny appearance. And of course over the years, copper turned green with the patina. Now they wanted the Parliament buildings, the Ontario Parliament buildings, to have that green patina, that old, established British look, but of course that would take years for the natural process of the patina to form. So they thought they would speed it up. So throwing salt would have been one idea. But
doing the opposite to a cathode.
yeah, you want it actually to be the anode. And so the story goes, they got the workmen to head up onto the top of the roof and relieve themselves onto the roof so that the ions in the urine would catalyze the formation of the copper patina. This is what they tell about the Ontario Parliament buildings. It's almost involved, and yeah, we won't want to say anything about the conditions. So that's the story, that they actually helped speed up the formation of the patina with a little bit of extra electrolyte solution placed on it. Okay, so that's corrosion in a nutshell. 100 things they could have done, but you got a bunch of workmen there, and hey, you gotta go.
Like, you're saving time, you're working harder, you're not leaving by the washroom, and you're peeing on a building.
Yeah, exactly. It was a really good engineering solution to the problem.
Donald Trump would be proud.
Okay. Well, there would be rain eventually. Any questions?
Oh, yeah, number 3 or 4 on making classes.
Okay. Do you remember what the question was?
It was the silver spoon one.
Okay, silver spoon. All right. So, the expression is, she's born with a silver spoon in her mouth. And literally, that would mean putting a silver spoon into a moist, acidic environment. So what do we mean by moist and acidic? There's going to be water present, and there's going to be H plus present because it's acidic. Not only that, it's implied that there will be some calcium 2 plus, not much because the calcium is supposed to be in your teeth, but maybe you've been eating sweets a lot, and you've been breaking down the calcium in your teeth, right? Because you've been eating sugars, and the bacteria on your teeth turn the sugars into alcohols. Alcohols are weak acids, and they dissolve your calcium. This is how you lose your teeth, by eating sweets. The bacteria turn the sugar you eat into an acid. The acid breaks up the calcium that's in your tooth. That's how it works. Okay, so presumably she's rich, but she's also got candy, and so there's some calcium 2 plus, there's some H plus, there's water, obviously, because it's in the mouth, and she has this silver spoon in her mouth. What happens?
That's what we wanted.
Okay, well, think about it. What are the possible reactions here?
I think it's like the silver oxide.
Okay, so one possible reaction is the oxidation of silver. How can we see if this is a reasonable reaction? What can we do?
We compare it to the other metal, Ca present.
Yeah, so the electrons would have to go to somewhere, right? Where could the electrons go?
Calcium,
They could go to calcium.
water.
They could go to water. Right? They can even go to hydrogen. Okay? So what do we need to do to see if any of these reactions are possible?
We look on the chart.
We need to look at our reduction potentials and the chart and see what we get. First off, let's see how much it costs us in energy to, let's see how much it costs us in energy